this video, I'm going to cover some more advanced programmatic concepts in R. So we're going to basically cover how to make a function in R and how to do if-else statements or conditional statements in R. So just as we've done before, I'm going to go ahead and set my working directory. I've got this walkthrough script that I'll post, and I don't have an R Markdown one for this because it's relatively new, so hopefully this will be helpful. I've got a lot of comments throughout here. So what we're going to do is we're going to work with some data from my own lab where we've done an experiment to look at the effect of temperature on meiotic recombination rate. And so we're going to read in the raw data from this experiment using this code here, and I'll share the data with this walkthrough video as well. And we're going to make an if-else statement. So this is a conditional statement, and you've seen if statements before where you have some sort of condition, and then you have a block of code in Shell or Perl where you say, you know, if it's true, you're going to do this, and if it's not true, you're going to do that. And this is sort of your else statement, and that's why it's called if-else. And I believe there's an extra S in there. And so in R, instead of it being a block, it's all in one set of parentheses, and then the first statement would be the condition that you're testing, the second statement would be what's going to happen if that condition is true, and the third statement is going to be what's happening if that statement is false. So this is your basic if-else syntax, and we can actually go over here to the help page, and we can say if-else, and press enter, and you can see this is the test, and this is what to do if it's yes, and what to do if it's no. So to cover this sort of default use, let's use this object X, where it's just a list of numbers from 1 to 9, and we'll go ahead and run that. Now we have that object over here in our environment, and now what we're going to do is we're going to do a basic if-else statement. So we're going to say if X is greater than 5, so we're running this on the whole vector, then return greater than 5. And you'll notice I've put this in quotes, so this is character value, and then alternatively return less than 5. So let's run that, and you'll see that I get this sort of less than 5 for the ones that are less than 5, and then as it becomes 6, it becomes greater than 5. Okay, I can store the output of that into an object called Y, and that Y is going to be over here in my environment. Similarly, if this were part of, say, a data set, I could add it as a new column to an existing data set, which you've seen in previous data manipulation videos. The other thing that we might want to do, so this is splitting our data basically into two different categories, similar to that cut command that we used in the data manipulation video using that Quakes data set. We may be interested in breaking our data down into more than two categories, and the way that we can achieve this is through what are called nested if-else statements. So we would use this basic same syntax that we've used here, but where we would normally put no, we're going to put another if-else statement to sort of split that no into two more categories. And so we can do this endlessly to split it into as many categories as we want. So let me show you how this would work. So here's using that same X equals greater than 5 test. If it's yes, we would say greater than 5. And if it's less than 5, we would do a nested if-else. And this new nested if-else is taking all of the values that are less than 5 and testing it against a new expression that it's less than 2. If that's true, it'll put less than 2. But if it's false, then that means the number falls somewhere between 5 and 2, and so we can put between 5 and 2. And so let's run that and see what happens. And you'll see, just like we got before, where we had, you know, these values were less than 5 and these were greater than, all of these values are still greater than 5, but then we get between 5 and 2 for a subset of values. So we've now effectively broken our data down into 3 categories instead of 2, using a single nested if-else statement. It's the same idea, but a slightly different syntax would be, instead of saying greater than 5 or less than 5, or somewhere between 5 and 2, we might want to just call them high, medium, and low. And we would do the same exact thing. We could say if X is less than or equal to 2, let's go ahead and take that part of the yes and split it into 2. And if it's less than 1, we'll call it medium, otherwise we'll call it low, and then if it's greater than 2, we'll call it high. So let's run this, and you'll see what happens is we end up with low and then no mediums and then high, okay? And that's just because of our x. So we could add in some 1.1. We need something that's between 1 and 2. 1.9. So let's run this. And we're still getting no mediums. So medium would be less than 1. And there we go. We don't have anything less than 1. So let's do 0.5, 0.75. Okay, and we'll run this. And now you can see that we have values below 1, so we have low, medium, and high. Okay. So both of these two nests are going to give you 3 different categories, but they're structured slightly differently. So this one's taking the no statement and splitting it further, and this one's taking the yes statement and splitting it further. Okay, so now let's return to the data set from my lab that I was mentioning earlier. So in this data set, what we're going to do is we're going to take the raw data and we're going to read it in and use nested if-else statements to classify it into crossover classes. So in this case, we've used phenotypic markers, yellow body, Y, which is signified by the letter Y, scalloped wings, which is signified by the letter SD, and then sepia eye color, which is signified by the letter SE. So each of these has a column, and then in the data set that we did, we basically just called it as a 0 or a 1, binary characters. If it's a 0, then it is wild type, and if it's a 1, it's a mutant, meaning that it has the particular mutation in that category. So what we're going to do here is we're going to say, let's start with the situation where all of them are equal to each other. So we have 3 different mutants, yellow, scalloped, sepia, and if yellow equals scalloped and yellow equals sepia, then that means all 3 of them are equal to each other, meaning that it's either 0, 0, 0 or 1, 1, 1, meaning that it is not an individual where we would have observed a crossover event. So when we're looking for recombination events, we're looking for individuals where 2 of the markers would not be equal to each other, signifying that the chromosomes had recombined in the previous generation. So what we'll do is we'll say this is our test, that everything's equal, and we're going to give it this label non-crossover. Similarly, we would have 2 different single crossovers. So we can have a crossover between yellow and scalloped, which we can call single crossover 1 or class single crossover 1, but yellow and sepia are still equal to one another. Alternatively, we can have a condition where yellow and sepia are not equal to each other, indicating that there's been a single crossover there. So we'll call those single crossover class 2, but yellow and scalloped are equal to each other. And then finally, we would have the case of a double crossover where yellow is not equal to either sepia or scalloped. So this would be the case of 0, 1, 0, indicating 2 crossover events, or 1, 0, 1 along the chromosome, indicating, again, 2 crossover events. Now, one of the things that I like to do whenever I'm doing this is, as a sanity, the last one, I will put something in there. I will say error. And the reason that I do this instead of just empty quotes is that I can then use this code to quantify it, and it should be 0, right? If I've accounted for all the possible variants, then I should have none that are going to return no once they've trickled through this nested if-else statement. So I can run this as sort of a sanity check. And then I'm going to store all of this. As I mentioned, you can store this into a new column called crossover class in my existing data set. Okay, so let's run this code. So let's first look at the data. So here you can see I've got date, file number, day, number of males, and then I've got that 0, 1, 0 or 1 for my different mutants. And this is the initials of the person who did it and who recorded that data, and then the notes. Okay, so we're going to add this new column called crossover class. And you can see now we have this column in our data that's populated, and for every single row it's going to tell us whether it's a single crossover type 1, single crossover type 2, a double crossover, or a non-crossover. So we've basically just categorized it into 4 different categories using this nested if-else statement. Now, again, I said that if it doesn't fall through this, let's label it an error. So let me run this, and that's great news. I get 0. And what this means is that none of my data comes through as error, meaning that every single row is assigned to one of these 4 categories and never assigned to error. So that's really good. The next thing that we're going to do, because we want to quantify this, is we're going to rerun this code. It's basically the same exact nested if else, except instead of putting a character label on it, non-crossover, single crossover, 1, 2, and double crossover, we're going to put numerical labels on it. So if it's a non-crossover, we're going to make it 0. If it's a single crossover, we're going to make it 1. And if it's a double crossover, we're going to make it 2. Now, in our case, each row in the data set is not an individual because they were lumped. So this is a record of 2 males, this is a record of 1 male, this is a record of 3 males, for example. So we're going to want to multiply the number of crossovers by the number of observations, which in our case comes from the column num males. In our data set, in the experiment that we did, we only scored this in male progeny, and that's why we're interested in this instead of the total number of individuals. So we're going to multiply 1 by that. We don't need to do 0 because 0 times any number is still going to be 0. And then we're going to store this in a new column called number of crossovers instead of crossover class. And again, just like we did before, where we stored the last ones as error, because this is numerical data, we're going to store the last ones as NA. And this has otherwise very similar syntax to the previous one. We'll add a new column that's going to be number of crossovers here. And you can see immediately that the double crossovers are going to be 2 times the number of males, which in this case is 4. This is a single crossover, which is 1 times the number of males, which is 2. So this is correctly working so that each row is telling us how many crossovers are associated with this particular column or row of data. Now, the last thing that we want to know is what is the recombination frequency of this? And in order to get that, let's go ahead and make a function to calculate percentage, because recombination frequency is the number of recombinants divided by the total sample size, which is effectively percentage. So we're going to make a function called percentage, and we're going to say it's a function. It's going to take an x and a y, so the sum of recombinants divided by the total number of progeny in this case, but we're going to use generic terms like x and y. And then you'll notice that we have this syntax here where we've got a code block, very similar to what you might have seen in Perl. And in our code block, we're going to have some object p that we're going to be calculating. That's our percentage, and it's going to take x and y and divide them, and then multiply the result by 100 and store it in an object called p. And then it's going to use this function return p, and that's what's going to be returned when you run the percentage function. So let's go ahead and run this. You'll see over here, I've got this new thing in my environment tab, which is functions, and I have a function called percentage, and it says it's a function that takes an x and a y. Okay. So now let's go ahead and use our function. So what I said is we want to calculate the total number of crossovers. We made this column called num crossovers to be able to count that, and we'll use the built-in operator sum so that we can get that. So the sum of total crossovers in this data set is 4,300. We can store that in a value A, and we've got that over here, 4,300. Similarly, we can take the sum of total number of progeny, which again, as I said, in this experiment was only males, so that's going to come from this num males column, and we can take the sum of that over this whole data set and store it in an object B. Okay, so now we have these two numbers, and we can use our percentage function to get the percentage of A and B. And we get something like 78.87%. Now, another way that we can use this, instead of taking these two things and storing them in objects and then running percentage on those objects, we can actually just run percentage directly on these two values. And it's a little bit more streamlined, but it's also kind of harder to read. So it really depends on what you would prefer to do. You can store them in objects first and then just run it on the objects, or you can just run it like this, and we get the exact same answer. Okay, we can even store that in a object, and you'll notice that now we have an object over here called percent that holds the value 77.87. So that concludes this video. What I'm going to encourage you to do is think of calculations that you do commonly and try and practice making a function for one of those calculations, just as we did in this walkthrough video.